It's available. So recording now. And so if you got questions, that's fine. Please feel free to ask the questions. That is not a problem. Let's just not use names here. All right. So let's continue on talking a little bit about SolidWorks. So we've done pretty much I think we've done all the tutorials I'm going to ask you guys to do. And let's do a few things where we talk about using SolidWorks a little bit beyond that. But one thing I want to talk about today is a concept called tolerances. And so tolerances, to talk about tolerances, we've got to lay down some base theory first, but let's talk about what tolerance is in the mechanical sense. When we're talking about tolerance, we're talking about mating parts, objects that are designed to fit together. Okay? And so when I'm designing things to fit together, the simplest thing to say is they can't really be the same size. I mean, they could, but that presents a number of challenges, and we'll see that, especially as we start 3D printing things for the final project. The idea of tolerance is the amount that something can vary and the parts are still functional. So if I'm trying to put two objects together, right, if I've got, for example, right, just a dry erase marker is one of the best things I know because I've always got one handy. There's going to be a tolerance associated with the inside diameter on the cap and the outside diameter right here on the stem that it connects to. There's going to be a tolerance associated with how much can this dimension, this diameter on this pin vary, and how much can the dimension inside this cap vary, and it still be functional. The larger the variation can be, the cheaper it is to make, cheaper it is to manufacture. And the more specific it's got to be, the more expensive to make that kind of precision. We'll talk about that as we go forward here. So again, tolerances are assigned in such a way that any two mating surfaces can fit together and be functional. And that's what I just alluded to here, is that to get, if I'm to say that if I've got, it's like the tip for this dry erase marker here, and if I'm to say that this diameter here is supposed to be and if I say this diameter is 0. It's not 0.25, it'd be 0.25 inches. If it's supposed to be exactly a 1/4 inch, right? 0.250000 inches, it's not. Right? If that's what it's supposed to be, I guarantee you we could put a micrometer on it right now and measure it. It's not going to be 0.25000. It's not going to be exactly a 1/4 inch. It'll be close. It'll be in the ballpark. And the tolerance specifies how close to that 1/4 inch can this be to still be functional. So it'll still interface with any cap that we want to put on it. So I could take, off this black pin, I could take the cap off of this blue pin and swap them. And I guarantee you they're interchangeable because there's appropriate tolerances have been set for the same make of pin. These are just different colors, but the parts are interchangeable. And that's because there's effective tolerances have been set. Somebody's looked at that and said, well, this one can be within, 1/1000th of an inch or whatever it may be, within that 1/4 of an inch. It's probably more like 5/1000ths of an inch or something like that. Okay. And again, you can, now with all that said, there are some methods that we could do to make sure that this is 0.250000 inches. It's not impossible to make it exactly a 1/4 inch or as close as we can. But what I would suggest to you is as you add more zeros or more significant figures, those who've had a laboratory class, as you add more significant figures, you increase the price. Right? Basically, it's kind of the simplest way to think about it. To get it as close as you can to a 1/4 inch becomes more and more expensive to do that. Doesn't need to be exactly a 1/4 inch. It just needs to work. Honestly, that's all it boils down to. It just needs to work. So how much can it vary and still work? That's our tolerance. Some terminology to specify here. So what we call the nominal size, that is just the call out value, if you will. That's what we specify. So if I go to a big box store, a home improvement store, and I am to buy lumber, and a standard size lumber will be a 2x4. Well, if you go put a ruler on a 2x4 off the shelf, it is not 2 inches by 4 inches. So you know this, right? It was close to 2 inches by 4 inches before it was dried, before it was put in the furnace and dried. So it is stable then. It's close to 2x4 at that point, and then it shrinks down. Or if it's not dried, if it's treated, they go ahead and cut it down to about the standard length that a dried plank would be. But that's your nominal size. That 2x4, it means that's nominally 2 inches by 4 inches. It's not exactly, and in fact, in lumber, because as I said, because it's treated, it shrinks. It's not 2 inches by 4 inches, but that's what we call it. It's a 2 inch by 4 inch. The basic size is kind of the starting point. So in the example of these pens here, right, these dry erase markers, I shouldn't call them pens, they're markers. There's going to be a basic size, probably, I don't know, maybe that looks like roughly in the neighborhood of 1/4 inch to me. So maybe that's your basic size, 0.250 would be your basic size. And then an actual size would be if I actually put a pair of calipers or a micrometer on this and actually measured that it's 0.249 or whatever it might be. That would be the actual size for the actual piece in front of you being measured. If you go to Lowe's or any other home improvement store and you go to the shelf and you look at their 2x4s and you go grab a tape measure off the shelf and you'll measure it, right? Unless you brought your own tape measure, either way it works. You're going to measure the actual size, which is not going to be 2 inches by 4 inches. Same thing if you went to the plumbing section and you pick up some PVC pipe. The nominal, you're going to have a nominal size. That's going to be what the inside diameter is based off of. There's going to be a basic size, again, kind of the starting place, and then an actual size when we actually measure one. So and what you'll find on something like PVC pipe, if you were to take a pair of calipers and measure the inside diameter on one end of that PVC pipe, that's the actual size on that end of the pipe. And if you flip it around and measure the actual size on the other end, they're probably not going to be the exact same. And something as cheap and widely produced as something like 2x4s or PVC pipe or PEX tubing, whatever it may be. When we're in, same thing here, right? There's probably going to be variation from the base all the way out to the outside diameter right at the very tip. Maybe that's design, but maybe that's just the variation in the manufacturing. So again, nominal size, basic size, actual size. So some basic terminology there to know. So how do we? So here's the good news. I'm not going to ask you guys to specify tolerances. I won't say it all, but in general, I normally don't ask you guys to specify tolerances. I'm only presenting the topic to you and asking you to think about it. And anytime anytime you're designing something to interface with, to mate, to connect to something else, and especially if we're going to be printing these, you want to think about what's a reasonable amount of tolerance to put in, and how can I design the basic size for something else that fits in something. How do we communicate that though? So if I'm sending this out, if I'm sending drawings out to somebody to manufacture, if I'm manufacturing the pen or the marker, and I need to send drawings out to somebody to manufacture caps for me, I need to specify the basic size of the inside diameter of this. And then I'm going to use some method of specifying how much bigger or smaller that the inside diameter can be relative to that basic size. How we do that, there's a number of flavors, and they all have their advantages and disadvantages. Which one should you use? I don't know. It depends on your scenario. Just have to see. But let's look at some examples of all of these, right? The limit dimension, for example. So the limit dimension is where you don't even specify the basic size. You just specify what's the largest the actual size can be and what's the smallest the actual size can be. The limits, right? The upper and the lower limits. Can be in inches, can be in millimeters, as you see here. But again, this is limit dimensions are going to specify the upper and lower acceptable value that a part can be and still function. And in this case, we'll see a type of drawing. We'll see a diagram similar to this multiple times today. Here we're saying if we just look at the cross section, the end of the external component, and the cross section, cutoff cross section of the internal component, and they're just specifying how big or small each one can be and still achieve the function that is desired. I see more commonly, rather than limit dimensions, when I do encounter tolerances, I typically will see plus minus tolerances, right? So with the plus minus tolerance, you specify the basic size, and then you specify how much above and how much below that basic size the part can be, communicating the same information that we just saw with the limit dimensioning. Here we're achieving the same goal. There's some advantages here. Here we can specify, hey, look, this is roughly, it should be 1.878, and it cannot be any larger than that. A plus of 0, and then a minus of, we're saying it can't be any larger than this, but it can be a little bit smaller and still function. Right? So that's what we call a unilateral, where you can't go above or you can't go below the basic size, but you'll specify how much you can go in the other direction. A lot of times we'll call out the basic size and tell you how much above or below you can go and still be acceptable. In both cases, these are examples of plus minus dimensioning. There's a special case of plus minus dimensioning that we can see. That's called this equal bilateral. And most of the time, when I think of plus minus dimensions, this is what I think of. The basic size is in the middle of a range, and so I can go a certain amount above that range or an equal amount below that range and still achieve what I need out of the part. The wider the values, like the wider that difference, the bigger the plus minus is, the cheaper it is to manufacture within that range. Changes, if I'm manufacturing something made out of plastic, changes in the humidity in the air will change the temperature at which that plastic melts and the viscosity of it as it flows into a mold or something like that. Just something as simple as the humidity in the air. And here in our state, we know that's right. That's going to vary from the hour. That would be enough to alter the size of something as I'm manufacturing it. So unless I've got a really expensive facility where I'm controlling the temperature and humidity inside a large facility, which is very rarely is that reasonable, I'm going to experience, as I manufacture something, I'm going to experience some variation. Tolerances then would specify to anybody I'm trying to communicate, here's how you make this cap so it fits on this marker, and here's how much above or below you can go. And again, just a variety of ways you can do this. This is kind of the most common. You call out the basic dimension in the middle and say it can be this amount above or below, and still be acceptable. Now, again, I'm not going to ask you guys to specify tolerances, but I am going to ask you to think about it. Okay. Angular tolerances, we're not going to deal with. I don't anticipate, unless it's a pretty specialized thing in one of your final projects, I don't anticipate we're going to have to worry about angular tolerances, but it is neat to think about. We can specify angles with smart dimensions in SolidWorks the same way I do dimensions, right? I can click between two lines and specify the angle between them. If it's not, if I've drawn a rectangle and it's already specified as 90 degrees, SolidWorks is not going to let me specify the angle there. But if I've just drawn two lines arbitrarily, I can specify the angle between them. Just smart dimension one, click on the other one, and it'll let me set the angle between them. You can specify tolerances with the, how much above or below a specific basic value that angle should be. You can do that in minutes and seconds, fractions of a degree. It's pretty rare, honestly, today, especially given modern calculators and how easy it is to do fractions and decimals. But it's still allowable. It's still understood. There's, here we're saying there's 30 or there's 60 minutes in a degree, and then there's 60 seconds in a minute of a degree. It works okay if I'm talking about something the size of the Earth. If I'm talking about something the size of a marker, we're going to talk about decimals of that degree, points, fractions of that degree, and how much above or below I can go. But either one works. Now, when you start getting into 3 dimensions, and if those of you that have ever drilled holes in large hunks of metal, you have some experience with those. If you drilled holes in wood, unless it's like a really thick piece of wood, it's not. If I'm drilling holes through really thin pieces of wood, the wood is soft enough. It's not super critical that I get that hole exactly perfectly straight, right? If I drill a hole and I'm trying to put something through that hole, as long as whatever I'm putting through the hole is much harder than the wood itself, I can kind of push it up and down and bend it and kind of force it in. The thicker that slab of wood gets, the harder that is to do. If you do this in metal, if you drill through a thicker slab of metal, that metal probably is not going to bend and be very forgiving. So it's really important that if I need that hole straight in that metal, it's very important that I drill that hole right straight in. And then you're going to get into a larger drill, something like a drill press, where it's basically on a handle and you can kind of control that head as it comes down. It keeps it straight, as opposed to just taking a hand drill and trying to get it straight, right? That works okay with wood. Metal, it gets to be a bit more. And so some different things to think about. So again, and if you don't have a lot of construction experience, not a prerequisite for this course, some of that's lost on you. You've not had experience dealing with those troubles, right? And so just kind of a diagram to try to illustrate some of that I'm talking about here. Let's say I've got something that's going to go inside of a hole. In the perfect ideal world, which doesn't really exist, that cylinder that's going to go inside this hole is going to be perfectly aligned right in the center of that hole every time, and the world is happy. And that's not how that's not how it actually works when we start putting things together. No, the cylinder, maybe because of what's going on down below or down above, the cylinder that's going inside the hole may be off-centered a little bit. How much can it be off-center and still be functional? How straight can this hole be and still be functional, right? These are all things that when I'm communicating really complex manufacturing to somebody, we have to think about these and think about ways that we can communicate how much plus or minus can this be done. And that is a real challenge. It's not trivial at all. Okay, but so again, it's not expecting you to do that level yet. But here's one thing I do expect you, probably the most important thing I'm talking about today is types of fit, right? Types of fit, because again, for your final projects, we're probably going to be 3D printing things for a client. It's probably going to be something that's going to attach to something they already have, or we're going to be printing multiple components that need to attach to each other. And we need to think about how are they going to interface with each other, right? So this is terminology that we can use moving forward. A clearance fit is where whatever is fitting inside is always going to be smaller than whatever it's fitting into, right? There's not going to be contact between the two surfaces. An interference fit, so the markers that I keep continuing to use as a good example because, well, it's handy and we've all probably picked up a dry erase marker before. This is what we call an interference fit. You really have to force that inside the other, right? And you want that tight seal because we don't want the marker to dry out. So you want an actual interference fit on something like this. And that's where the internal member is actually larger than the external member. They're going to have to be forced together. And which one do you need? Well, it depends on what we're building. In this case, the perfect example where I need an interference fit. If I want, for example, though, this to be able to rotate freely, to just put it on there and just spin it, that would be an example where I'd want a clearance fit. I don't want the two surfaces to actually touch. I want them to be able to rotate freely inside each other. A transition fit is where it's not important, right? It's not critical one way or the other. It can work just fine if we have to force them together. It can work just fine if we don't have to force them together. Okay. If it's acceptable to apply a large amount of glue to the two, if I need to really seal them up, or if I'm going to weld one to the other, right? So I know I'm going to use some other means to join them, not just pushing them together through friction. A transition fit would be probably acceptable in some cases like that, right? The rookie mistake, the line fit, that's what we call the rookie mistake. That's where you just say, oh, well, just make them the same size, right? You specify a basic size where they're the same size. You know what? This fits in this. Just make this a 1/4 inch and the inside hole a 1/4 inch, and it'll work. That's a line fit. You specify one basic size that's the same as the other one. And then what you're doing is you're just gambling that whatever process is used to manufacture it works exactly, perfectly. Again, you're assuming you're going to get a bunch of zeros out there. You won't, right? You won't. If I'm designing something to fit inside something else, I want to think about, how do I want them to fit? Do I want them to fit freely? Then design for a clearance fit. So whatever's fitting inside, make it a little bit smaller than what it's going into, right? If I want, what we do a lot of times with 3D printed parts, if you send me something and sometimes I'll think to ask, how much did you think about tolerances? What kind of fit did you design here? If it's early in the semester, it's like your first prototype and it's something small, I don't mind and you send me a line fit, I don't mind printing them and handing you sandpaper when I hand them to you, because you're going to have to sand one to get it to fit inside the other, most likely. I say that. I do have one really nice printer out there that I've seen it make line fits and they fit perfectly, and it takes away my thunder of handing you sandpaper and say, here, lesson learned, right? Don't make a line fit unless you don't care, right? If you actually care how they interface together, you need to think about, do I want an interference fit or do I want a line fit, or do I want a clearance fit? A lot of times, if we want a good snug fit, right, what we'll do a lot of times is we'll actually send them to the printer as a line fit, and then we'll go ahead and sand them to get the type of fit we want, right? We'll normally have that conversation. If we send them to the printer as an interference fit, and sometimes we have to really sand a lot of material off to get them to fit the way you want them to. So a lot of times what we'll do is we might cut just the pieces that are going to fit together out of your entire design, not print the entire design, just print the parts that are going to fit together, and just make sure that you get the fit that you're going to want to get out of that. Then we can mess with the tolerances there and go from there. Our printers in general will print to fractions of a millimeter with lots of precision. You don't get that out of most manufacturing processes, by the way. So it's a wonderful advantage. It will spoil us also, but basically to the nearest tenth, let's see, I always say to the nearest tenth of an inch or nearest millimeter, somewhere in that ballpark. It's really the 0.05 inches roughly. Okay. Anyway, questions here so far? Yes.
What are line fits used for in industry, or are they at all used in industry?
That's why I say they're rookie mistakes. We normally avoid them. Yeah, it's because again, it comes down to if it's something enormous, right? If it's something enormous, there's no way to force them together, right? Or yeah, you're gambling when you specify a line fit. You're gambling that's going to work and work the way you want it to. Other questions? Awesome. Let's see what else we got. Summary. Several methods we can specify tolerances on a drawing. Again, I'm not going to ask you guys to specify tolerances on a drawing. You can, I don't mind it. Limit tolerances where you specify the upper and lower maximum values or minimum values, that's fine. Plus minus is where you call out the basic size and how much above or below is acceptable. These are all good. Really what I want you to do is think about though, right? So if I want these two parts to fit, if I want a clearance fit between these two parts, then you probably want to make one about 1 millimeter smaller than the other one. And that'll, when we send it to just about any of our printers, that'll guarantee a complete clearance fit. And you could get tighter than that. We could, a lot of times a 0.5 millimeter difference normally will get us there, but okay. All right, guys, so let's talk about today's assignment. I'm going to go ahead and stop recording in case this video I attach it to a different assignment later. So I'm going to stop recording.